Hey there, class. This is our SPSS walkthrough for Factorial ANOVA with no interaction effect. So if you go to the Canvas website, we're going to go through this example in the video, the example two-way ANOVA with no interaction effect. So you can follow along with this output here. We'll go through this example in this video. The data set that's using the example is right here. Also give you the data in the the data set's here, sorry. Also give you the data where you could type it in the example here. So we'll talk about that in a minute. And then there's also a write-up for this two-way ANOVA with no interaction that's available on Canvas as well. So you can see how a result section, would look. If you want step-by-step instructions, they're available on Canvas too. Steps for running a Factorial ANOVA and SPSS. We're going to go through this top part in this video. The bottom part is for the simple effects analysis that we'll do if we have an interaction effect. So if you want to follow along with the example here, so in this example, the dean of the college wants to investigate whether the frequency of computer lab use over a 4-week period differs for a sample of 30 students. So the dean wants to investigate whether computer lab use differs in terms of the type of student who uses the lab, whether they're a doctoral or master's student, and the time of day the student uses the lab, whether it's on the weekends, the mornings, or the evenings. So in this scenario, the dean wants to investigate an interaction hypothesis. So we can think of this as either, do differences in time of the computer lab use depend on whether it's a master's or doctoral student, or do differences in computer lab use between master's and doctoral students depend on the time of day that the lab is used. Since this is the example with no interaction effect, we're going to say that that doesn't matter. But as you can see in this example, we have two independent variables. The time of day the student uses the computer lab, whether it's in the weekends, the mornings, or the evenings, and the type of student who uses the computer lab, whether it's a doctoral or master's student. So this is why it's a two-way analysis of variance. We could think of it as a 2x3 analysis of variance, because we have 2 levels of our degree factor and 3 levels of our time factor. That's why we might call it a 2x3 between subjects factorial analysis of variance. So the raw data are given here. You can also see on here, I did a screenshot of how the data would be typed into SPSS, so we can look at that too. Remember in SPSS, each row in SPSS represents an individual, and each column represents a variable. So our 2 independent variables was the degree type of the student, whether they were master's or doctoral level student. Our other independent variable was the time of day the students were using the computer lab, whether it was the morning, the evening, or the weekend. And our dependent variable was their average computer use over that period of time. So we can see here, person 1 was a master's student who used the computer lab on the weekend for an average of 2 hours. We go back to our raw data here. We have person 1 here. They're a master's student who used the computer lab on the weekend for 2 hours. We also have this student. They're a doctoral student who used the computer lab on the weekend for 10 hours. So we could see how we would enter that person is going to be right here. Right, so there are doctoral students, or degree type 2, who used it on the weekend, which I labeled time 1, and used it for 10 hours. If you're not familiar with how they're labeled, you can always go to the variable view tab, and then what did you assign the values? 1 was weekend, 2 was morning, 3 was evening, and then 1 was master's, 2 was doctoral students. You could assign them either way. You could have done 1 doctoral, 2 masters. Your results are all going to be the exact same. Just however you want to keep up with it. So notice how the data are typed in. You can practice typing in the data yourself, and then check that you have the same as what I did too. So once we have the data entered into SPSS to run the analysis, we go to Analyze, General Linear Model, Univariate, and we'll bring our dependent variable, the time use, over to our dependent variable box. And then we'll bring our 2 independent variables, the time of day and the degree program, over into our fixed factors box. And you can read in the notes the difference between fixed and random factors. We're going to talk about fixed factors here. We'll click on the EM means tab, and let's display our means for all of our groups there. And we'll just say continue. So these are going to give us our main effects for our degree and time. Let's also, if you're using SPSS 24 or lower, this EM means selection that we just selected was over here in options. In options here, we're going to get descriptive statistics, estimates of effect size, and homogeneity test. We actually probably don't need the descriptive statistics when we ask for the main effects, but it doesn't. It's not going to hurt anything. And we could also ask for post hoc test for our time of day variable. We don't need post hoc tests for degree because there's only 2 levels, master's, doctoral. But time of day has 3 or more. It has weekend, evening, and morning. So we could request like 2 post hocs, for instance, is what I requested in the example online. So we'll click continue. We'll click OK. And here are our results. Here's our descriptive statistics. These are always good to request because we want to know. Remember, there were 30 individuals. There were 15 doctoral, 15 master students, and then 10 broken up over the weekend. So we just want to make sure that, if we had 16 in one, 14 in another, that would say, oh, we had something miscoded. We could go back and check that out. The first thing we'll look at then is this Levine's test of equality of variance. This is one of those tests where we want to fail to reject the null hypothesis. It's a null hypothesis in this case is that the variances across the groups are equal, and that's what we want, right? Is that the variances, really the population variances, are equal in each one of the groups. If you're using SPSS 25 or later, they added 3 additional tests. SPSS 24 and lower just had this Levine's test based on the means. 25 and higher added some robust versions of the Levine's test based on the median, based on the trim mean. One of the criticisms of Levine's test is it's not as powerful if you don't meet the normality assumption, so if your data aren't normally distributed. And so the test based on the median or based on the trim mean is supposed to make up for that. In this case, we come to the same conclusions either way. My recommendation would be report the test based on the mean. If you're concerned that your data aren't normally distributed, use the test based on the median and just report that you used the Levine's test based on the median would be the one I would look at next. If you want some more information about the differences between these in the output, in my annotated output here, I provided a link here to some additional information about these different tests if you're interested in that. So going back after we look at the Levine's test, the next thing we always do first after that is look at the interaction hypothesis test. So SPSS represents that with a product term, so degree times time here. We'd move on over and we'd see that the interaction term is not statistically significant. It's not surprising since this is the video with what we do if there is no interaction effect. So if the interaction is not significant, then we're going to interpret in these main effects. If it is statistically significant, we're going to ignore these main effects and do a simple effects analysis. So since the interaction term is not statistically significant, this is really saying that the time of the computer lab use, whether it was the morning, weekends, or evening, that did not depend on the type of student who was using the computer lab, whether they were master's or doctoral students. So that since the interaction term is not significant, we're going to then interpret then the main effects. If we look at the main effect for degree, it is statistically significant. So it's saying that there is a difference in computer use time between master's and doctoral students. Since there's only 2 levels here, we could look at then the main effect. We could look at the means for then the main effects, which are given here in the estimated marginal means that we requested. We see that doctoral students use the computer lab more than master students, which probably isn't a big surprise. In the example write-up, in my annotated write-up here, also give you, so what we could also do is calculate Cohen's d effect sizes for that difference. So we could take the mean differences that were given in that marginal means table. Oh, I think it's down here. The mean for doctoral, the mean for master students, subtract them, and then divide by the mean square error term that's given here. And we could calculate a standardized mean difference. And that's what I did here. So that's just saying that doctoral students use the computer lab over 1 standard deviation more than master's students. The one way the between subjects effects have also gives you a partial eta squared statistic. So you can see that 29% of the variance in computer lab use can be explained by the degree level of the student. And you'll see that in, you can see when I ran it here, we found the same thing. So if you're going, if you have just 2 levels, we could just, to calculate an effect size or a standardized mean difference, a Cohen's d between them, we would subtract the 2 means and then divide by the square root of our mean square error term, which is given in this table here. So our estimated marginal means give us our main effects for degree, and then here's our main effects for time as well. If we look at the F-test for time, it's saying that there is a significant difference in computer lab use across the 3 time periods. Since it's 3 or more time periods, we need a post hoc test to look at the difference between those groups. It looks like here, just looking at the raw means, you can see students use the computer lab more on the evenings than they did in the morning or the weekends, is what it looks like here. But we could request some Tukey post hoc test, and we can see that, yes, students use the computer lab significantly more in the evenings than they did on the weekends. And so we have a significant effect here. And they use the computer lab significantly more on the evenings than they did in the morning. The p-value is significant here as well. So there was no significant difference between the morning and the weekend. So it's saying that, you know, evening time is significantly different than morning or weekend time. We can also calculate Cohen's d standardized mean differences effect sizes. For these pairwise comparisons, we would take the mean difference here, 7.5, divided by the square root of the mean square error term that we got from the 10.167, and we would get Cohen's d effect sizes for those differences. If we look at, I calculated those by hand in here too. So you can see that students use the computer lab over 2 standard deviations more in the evenings than they do on the weekends, and use it almost 1.5 standard deviations more in the evenings than they do in the mornings. And so that is, there's also a partial eta squared effect size we can interpret here too. So it's a variance explained effect size. So the time of day students use the computer explained around 54% of the variation in computer lab use time. Now remember, partial eta squared tends to give an overestimate of the variability. If you look in the Factoral ANOVA notes, I give you how to calculate omega squared for these effects. You have to calculate it by hand, and it gives you these so you can kind of get an idea of the amount of variance explained. It also gives you an overall variance explained for the entire model. So the type of students, whether they're a doctor or master, the time of day, and the interaction between the type of student and the time of day explained around 63% of the variation in time of computer use time. So this would be an effect for the entire model. So there's the overall effect and then an adjusted effect. So probably around more like 55% of the variation. This would be eta squared and partial eta squared for the entire model. So that is basically what we would do if for a factorial ANOVA with no interaction effect. Remember, the first thing we do is look at the interaction, the significance over the interaction term. If it's not statistically significant, then we'll go in interpret these main effects. If it is statistically significant, we'll see in the next video, then we'll perform the simple main effects analysis. I hope this was helpful. As always, if you have any questions or concerns, please email me or post to the message board. Thank you.